Solving general chemistry problems. Electrochemistry. This would be a common question to encounter in general chemistry. What is the standard cell potential for the cell described here between aluminum and silver using standard cell notation? Well, the answer is plus 2.462 volts. Do you know how we can determine that without actually building the cell? Here would be another question. What is the standard cell potential in the cell formed by the cerium 4 plus cerium 3 plus couple and the iron 3 plus iron 2 plus couple? Well, the answer is plus 0.95 volts. Can you interpret the language of the question to find this answer? Another question could read as follows. Use the following half cells to form an electrochemical cell under standard conditions and connect them to a voltmeter as indicated. Copper 2 plus connected to the negative terminal and manganese 2 plus connected to the positive terminal. What voltage will be measured by the voltmeter? So how do we interpret this language? Well, the answer, it turns out, is minus 1.52 volts. Let's look at how we can make these theoretical predictions regarding electrochemical cells in their standard state. Electrochemical cells are naturally partitioned into two parts, the cathode and the anode, or in other words, the reduction reaction and the oxidation reaction. We can, in principle, combine any reduction reaction with any oxidation reaction to form a complete electrochemical cell. Theoretically, this is how we can approach the study of electrochemistry. We can envision any electrochemical cell as being made up of two half cells. These half cells can be denoted in different ways. Now consider the Daniell cell we discussed previously. It has a zinc anode and a copper cathode. Perhaps the briefest way to describe them is to refer to them as the zinc 2 plus redox couple and the copper 2 plus redox couple. Some of the other half cells we looked at previously include the H2H plus couple and the silver chloride couple. Note how this notation only denotes the redox active participants. It says nothing about whether or not it is behaving as an anode or cathode in a particular implementation. It says nothing about concentrations or pressures or phase. But in many situations, it provides sufficient information to carry on a useful consideration of the situation being discussed. We might also use standard cell notation. For instance, the zinc 2 plus couple might be described as zinc 2 plus 1 molar, which provides more information. In this case, it implies we are also considering its anodic behavior. By contrast, the Fe2 plus Fe3 plus couple could be rendered as Fe2 plus 1 molar, Fe3 plus 1 molar platinum, if we were considering it to behave cathodically. Concentration information and the presence of the platinum inert electrode are now given. A final and important way to record this half-cell information is to write out the chemical reaction that is occurring. We could write zinc solid goes to zinc 2 plus 2 electrons, or copper 2 plus 2 electrons goes to copper solid. These are, respectively, the appropriate oxidation and reduction reactions in the Daniell cell. In that cell, the oxidation of zinc and the reduction of copper are occurring. We measure a potential difference of 1.10 volts between them. How much of that comes from the zinc reaction and how much from the copper? The answer? We don't know. We cannot measure the voltage of a single half-cell reaction. We can only measure the difference between two of them. We could conceivably measure and record the potential difference between all possible pairs of electrodes. The tables would be enormous. Instead, it has been decided to assign the potential for one reference electrode to be 0.0000 volts exactly, and then measure everything else relative to it. By convention, that reference electrode is chosen to be the H2H plus couple. By setting up an electrochemical cell with this reference electrode connected to the negative terminal of a voltmeter, we can take the measured potential, whether negative or positive, and attribute it to the reduction behavior of the other cell, what can be called the test cell. If we were careful to ensure that both half cells were operating at standard conditions, 1 molar, 1 bar, we would measure the standard reduction potential. This is the potential assigned to the test cell, measured relative to the reference hydrogen cell, when the test cell is connected as if it were a cathode at which reduction could be occurring. In this manner, we can create a table of standard reduction potentials. Connect any cell, make sure it is at standard conditions, to the positive terminal and tabulate the measured potential. Some half cells will behave cathodically when up against the H2H+ couple, and the measured potential will be positive. Other cells will behave anodically with respect to the H2H+. This will be recognized by the measured negative potential. But all half cells can be placed into this table. The experiment used to test each one connects them to the positive terminal of the voltmeter. It is as if we were assuming it would behave as a reduction. This table, then, is a table of standard reduction potentials. All entries are written, therefore, as a reduction reaction. Many entries appear with negative potentials. All that this means is that when compared to the H2H+ reaction, such a reaction will be an oxidation. Now here is such a table. This one is comparatively small. More extensive ones are available. Each entry is written as a reduction. However, recall that a redox reaction requires one reduction and one oxidation. Any reduction operating in reverse is an oxidation. So any redox reaction can be formulated by combining any two reactions from such a table. One reaction will operate as a reduction. The electrode where it operates will be called the cathode. And the other reaction will be the reverse reaction of another here in the table. It must be the reverse because then it can be an oxidation, and its electrode will be called the anode. As an example, consider the iron 3+ iron 2+ couple connected to a cell with the magnesium 2+ magnesium couple. The reaction, which is higher up in the table, will be the one that functions as a reduction. The lower one will function as the oxidation. Therefore, we connect the iron cell. It will have an inert platinum electrode, and that will be how the electrical connection is made, to the positive terminal of the voltmeter, and the magnesium to the negative terminal. Iron 3+ will be converting into iron 2+, and magnesium will be converting into magnesium 2+. The standard cell potential, everything present at standard conditions, will be the difference between the two. Cathode minus anode, 0.771 minus a minus 2.372 is equal to 3.143 volts. The positive potential confirms we have correctly attached the reduction to the positive terminal of the voltmeter. Now, this is a general approach to constructing standard cells. Take any two reactions with all participants at standard conditions. Connect the one that is highest in the table, has the most positive standard reduction potential, to the positive terminal. It will be the cathode, and the measured potential will be cathode minus anode, or most positive minus least positive. An example, the persulfate-sulfate couple and the cobalt 3+ cobalt 2+ couple. Here are the reactions. The persulfate's reaction is plus 2.01, reaction potential is plus 2.01 volts, cobalt is plus 1.92 volts. The cobalt cell will be the anode, persulfate the cathode. The overall cell potential, E naught cell, is 2.01 minus 1.92, or plus 0.09 volts. Another example, cobalt 3+ cobalt 2+ and strontium 2+ strontium. Potentials are respectively plus 1.92 and minus 2.899. This time, cobalt is the cathode and strontium the anode. Cell potential is 1.92 minus a minus 2.899, or 4.82 volts. Remember that if we were ever to connect these cells up backwards, the magnitude of the measured potential would be the same, but it would be its negative value. Another example, aluminum 3+ aluminum and magnesium 2+ magnesium. Potentials are respectively minus 1.662 and minus 2.372 volts. This time aluminum is the cathode and magnesium the anode. We're looking here for most positive, which may very well be negative. It is the relative magnitude that is important. Cell potential is minus 1.662 minus a minus 2.372, or plus 0.710 volts. One warning, some tables are organized with the most negative reactions at the top and proceed down to the most positive. Make sure your most positive reduction potential is connected so as to be the cathode. One other warning, and it should by now only be one of historical significance. A half century ago, these tables were of standard oxidation potentials. The numbers were all of the opposite sign. The reactions were all written as oxidations. The reference cell, the H2H plus half cell, was connected to the positive terminal and the test cell to the negative terminal. You could still use the tables, but you should be aware of the way things could change. This would only arise if you were looking at data or journal articles from many decades ago. We might also want to write down the overall cell reaction. And this is something like when we balanced redox reactions, except the hard work is already done for us. The half reactions are already balanced. We just need to scale the reactions so that they have the same number of electrons, reverse the anodic reaction so it is an oxidation, add them together, and cancel any excess items. Recall the persulfate cobalt cell we looked at. Here are the reactions. Persulfate is the cathode. The cobalt reaction will be multiplied by 2 to balance electrons. It will also need to be reversed so it can be an oxidation. Let's add them together. We scale and reverse the cobalt equation. Here is the balanced redox reaction between persulfate and the cobalt 2 plus ion. Now here is another example, the aluminum magnesium cell we looked at above. We need to scale both reactions, aluminum times 2 and magnesium times 3. Reverse the magnesium reaction since it is the anode and is an oxidation. Here is the balanced redox reaction. Now there is one more thing you can do with these standard reduction potential tables. How would you answer questions such as these? Could you safely store a 1 molar solution of HCl acid in a copper container? What about in a zinc container? Or what would happen chemically if you placed a copper bar in a 1 molar solution of zinc chloride? What would happen if you placed a zinc bar in a 1 molar solution of copper chloride? How do the standard reduction potential tables help with interpreting these scenarios? Note the major difference between these situations and the previous situations encountered when forming electrochemical cells. For a cell, both oxidation states are present, for instance, both copper metal and the copper 2 plus ion, or both zinc metal and zinc 2 plus ion. As such, the reaction is prepared to go either way, forward or reverse, reduction or oxidation, depending upon the driving force of the other half cell. Not so here. Here, each substance is present in only one oxidation state, for instance, just copper metal and just zinc 2 plus ion. We still have to couple an oxidation with a reduction. In the electrochemical cell, a reaction of some sort will always occur. A particular half cell will go forward or reverse, but in these different questions it is possible to have no reaction occur. Identifying whether or not a reaction will occur is the goal of this analysis. The first step is to identify the reactants we are to consider. In the first example, it was acid and elemental copper. Now find the relevant reduction reactions. The acid reaction is our reference standard, the H plus H2 reaction couple, but only H plus is present. The copper reaction is the copper 2 plus copper couple, but only copper metal is present in the situation. Here are both relevant entries from the standard reduction potential table. Note the actual species present according to the question: copper metal and hydronium ion. The question is, will they react? If they will, then copper would not be a good container in which to store the acid. The only way for copper to react is to be oxidized. The only hydronium reaction is to be reduced. Notice that the corresponding cell potential would be cathode minus anode, which is 0 minus 0.34 minus 0.34 volts. The potential would be negative. This indicates that the reaction is not favored. In fact, nothing would happen and copper would be okay in which to store such a solution. What about the zinc container? The reaction will involve the H plus H2 couple and the zinc 2 plus zinc couple. So what is actually present? Zinc metal and hydronium ion. Zinc can only act to be oxidized, hydronium to be reduced. The corresponding cell potential would be 0 minus a minus 0.763 or plus 0.763 volts. The potential would be positive, reaction would occur, the acid would quickly consume the zinc container, not a good material in which to store acid. Look again at the table. Note that you can have a reaction between two substances if one can be reduced and the other can be oxidized. In addition, the oxidation reaction must lie below the reduction reaction, more negative, less positive. So what about the copper metal in a solution of zinc ion? The equations are shown here. Note what is actually present: copper metal and zinc ion. Copper can only be oxidized, but that reaction lies above the zinc reaction, and the zinc ion can only be reduced. Therefore, no reaction will occur. What about the other way around? Zinc metal into a solution of copper 2 plus ion. Now the zinc metal can only be oxidized and the copper ion can be reduced. They occur correctly in the table. Copper is above zinc. So yes, reaction will occur. The zinc metal will start to dissolve and copper will start plating out on the zinc metal. So bear this in mind. A substance on the left-hand side of these tables will react with something on the right-hand side if the right-hand side substance is lower, more negative. Again, watch out for tables that go from negative to positive. No reaction occurs if the right-hand substance is higher, more positive. Also, there would be no reaction if you have two substances on the same side. We must have a reduction coupled to an oxidation. For instance, what about placing some lead sulfate in a solution of cadmium chloride? Or what about dropping a piece of silver in a solution of sodium fluoride? In both cases, the only thing, according to the tables we've looked at so far, that can happen is, in the first case, both lead and cadmium can be reduced. They both can consume electrons. But there is nothing to provide those electrons by being oxidized. And just the opposite happens for the silver in the fluoride solution. Two reactions to provide electrons, but nowhere for them to go. One word here. In general chemistry, you will need to solve problems based on the data provided to you. This is particularly true in exam situations. There may be additional reactions that might adjust our conclusions above, but I've chosen them, given the table presented earlier, to emphasize this concluding point that is correct. You have to have an oxidation and a reduction together for a redox process to occur, and the reduction potential of the reduction process must be higher than the reduction potential of the oxidation process. Then redox chemical reactions can happen.